Hello everyone, this unit will be demonstrating the integration of rational fractions, particularly for denominators having repeated linear factors. For repeated linear factors, if we have the integral of a function of x all over x plus a and the whole quantity is raised to n times dx, we could rewrite this or resolve the rational fraction of the integral into partial fractions. So this will be equivalent to the integral of the whole quantity a all over x plus a, that will be raised to 1, plus b all over x plus a raised to 2, plus d all over x plus a and the whole quantity will be raised to 3, plus n all over x plus a and the whole quantity will be raised to n. A, b, d, and n are constants that have to be determined. Let us illustrate that by evaluating the integral of v cubed minus 1 all over v times the quantity v plus 1 cube times dv. If we will consider the rational fraction of the integral, we could resolve this into partial fractions. We could write this as equivalent to a all over v plus b all over v plus 1 raised to 1 plus d all over the quantity v plus 1 raised to 2 plus n all over v plus 1 and the whole quantity will be raised to 3. We now multiply the least common denominator, which is v times the quantity v plus 1 raised to 3, so that we could clear out fractions. And multiplying the least common denominator will give us v cubed minus 1 equals a times the quantity v plus 1 cubed plus b times v times the quantity v plus 1 squared plus d. We multiply v, since v plus 1 quantity squared cancels out, we only have now a v plus 1. And for the last term, v plus 1, the whole quantity will be raised to 3, will also cancel out. So what remains will be plus n times v. So with this identity, we were able to clear out fractions. After clearing out fractions having this identity, the next step is we try to put the values of the roots of the factors of the equation. Let's say v is equal to 0. If v is equal to 0 and then we substitute that into the identity, we could solve the value of a, which is negative 1. And another root of this identity or the equation is v is equal to negative 1. Substituting v equals negative 1 into the equation, we could solve immediately for n. N now will be equivalent to 2. If we expand our identity equation, we will be taking this equation. And to solve for the values of b and d, we could equate the coefficients of like powers in our identity. For instance, if we will equate the coefficients of v cubed, it means that the coefficients of v cubed on the left side of the equation must be equal to the coefficients of v cubed on the right side of the equation. For this, we could see that on the left side, the coefficient of v cubed is 1. So that will be 1 is equal to the coefficients of v cubed on the right side of the equation. The first that we could see is the coefficient of v cubed, which is a. So that will be equal to a plus. And another, if we try to see and look for another v cube, we could see that we have a b as a coefficient, so we complete our equation. Since we know that a is equal to -1, we substitute that into the equation. So we get 1 is equal to -1 plus b. Here, we could solve for the value of b. b is equal to 2. If we equate the coefficients of v squared, it means the coefficients of v squared on the left side of the equation must be equal to the coefficients of v squared on the right side of the equation for identity. For v squared on the right side, we could see that we do not have a v squared, so that will be 0 on the left side. And on the right side, we could have 3a plus 2b plus d. And it follows, saying since we know the value of a, which is -1, and b is +2, we now can solve for the value of d, which is -1. Knowing the values of our constants, we now can substitute that in the partial fractions equivalent to the rational fraction of our integral. So in the first place, we try to resolve this as the integral of the whole quantity a all over v plus b all over v plus 1 plus d all over v plus 1 squared plus n all over v plus 1, and the whole quantity is raised to 3. We were able to solve for the value of a, and that a is -1, the value of b is +2, the value of d is -1, and n is +2. From here, we will expand it further so that we could easily integrate each of the terms of the integral, so that this will become negative integral of dv over v, which is the first term, plus 2 times the integral of dv all over v plus 1, minus the integral of the quantity v plus 1 raised to -2 dv. And the last term, if we expand that, that will become plus 2 times the integral of the quantity v plus 1 raised to -3 dv. If we look at the first term could be integrated by the logarithm formula, and the result is negative ln v. For the second term, we also can integrate this by the logarithm formula, which gives +2 ln of v plus 1. The third term, we could solve this by, or integrate this by the general power formula, and the result is +1 all over v plus 1. And the last term will also be integrated by the general power formula, and the result is -1 all over v plus 1 raised to 2 plus c.